Okay, so in the last few videos, we talked about the comparison test and the limit comparison test. And then we've also done the nth term test for divergence and the integral test. Now we want to look at another test for a different type of series. And the type of series we want to work with is what's called an alternating series. Don't worry about the test just yet. I want to do a few examples first. But suppose we have some series that looks like this. Negative 1 to the n, 1 over n squared. If I actually write out the terms of the series, well, we'll start with n equals 1 and go up to infinity. When n is 1, that's negative 1 to the 1, which is negative, over 1 over 1 squared, so that's negative 1. The next term, when n is 2, negative 1 squared is positive 1, times 1 over 2 squared, which is 4, and you get 1/4. And again, keep in mind, this is not the sum of the series, this is the terms of the sequence, which we would add together. But if I plug in n equal 3, I get negative 1 cubed, which is negative again. 1 over n cubed, 1 over 3 squared is 9, and I get negative 1/9. And clearly this will keep alternating. Next will be positive 1/16, negative 1/25, and so on. So essentially, I have a regular sequence, 1, 1/4, 1/9, 1/16. I wrote 1/12, but it's 1/25. But then the signs alternate, negative, positive, negative, positive, negative. That's an alternating series. But sometimes we can have a series that looks like maybe negative 1 over 2 to the n, which doesn't necessarily look like an alternating series, or at least it doesn't look like that. But if I algebraically manipulate this, that's the same as, since that's a fraction raised to a power, negative 1 to the n over 2 to the n, which I can then write as negative 1 to the n times 1 over 2 to the n. Now that's in the same form as this one, and this is kind of how we write out our alternating series. Sometimes you will have series written like this, where you'll have to manipulate them to get them into this form, because when we get to the test over there, they have to be in this form where the negative 1 is out in front. A lot of the time, most of the ones we're working with, they'll actually already be set up like this to show their alternating series, but be aware that doesn't have to be true. Sometimes you can algebraically manipulate them. Also be aware, suppose you have a series like, we'll say, n equals 1 to infinity of sine of n. We'll just do sine of n. That's it. Now, I'm not actually going to figure that out because I don't have a calculator, and those will just be a bunch of messed up decimals. But if I plug in n equals 1, I get sine of 1, sine of 2, sine of 3. And we understand how the sine wave works. Sometimes it's positive, sometimes it's negative. So if I actually listed out the terms here, some would be positive and some would be negative, and they bounce around because it's periodic. That is not an alternating series. Just because a series goes positive and negative does not mean that it's an alternating series. To be alternating, you have to have this negative 1 to the n or negative 1 to the n plus 1 out in front. If you can't write it that way, then it's not an alternating series. Something like this, you clearly can't do this because it just bounces around all the place all the time. So that's not an alternating series. But once we get an idea of what an alternating series is, now we actually want to know when they converge and when they diverge. So we have the alternating series test here. If you have an alternating series, depending on how they're written, sometimes it's negative 1 to the n, sometimes it's negative 1 to the n plus 1. But essentially, you pull out the negative 1 to the power, and then you're left with times a sequence a sub n. If a sub n is greater than or equal to a sub n plus 1 is greater than 0 for all n, so the terms are getting smaller. So if the terms are getting smaller, or the terms of the sequence a sub n is decreasing, and if the limit of the terms of the sequence is 0, then the series converges. And again, we keep on stressing conditions of tests and conclusions of tests. In this case, this test can't show you divergence. The only thing it shows is convergence. There's a trick that we can see that will work a lot of the time if this is inconclusive, but as far as this specific test goes, two conditions, the terms of the sequence have to be decreasing, and the limit of the sequence has to be 0. If that's true, it converges. Otherwise, the test is inconclusive, but there's a trick that we'll usually use if the test is inconclusive. So, suppose we have the series, we'll go with n equals 1 to infinity, negative 1 to the n plus 1 times 1 over n. And in this case, just to write out the first few terms just for this one, when n is equal to 1, you get negative 1 squared, which is 1, over n, which is 1, so you get 1. Next term, when you plug in 2, you get negative 1 to the 2 plus 1, 3, which is negative 1 over 2. And then it will alternate plus 1/3, minus 1/4, plus 1/5, etc., etc., etc. This looks just like the harmonic series that we had before 1 over n, only now the terms alternate positive and negative. This is actually called the alternating harmonic series because it's a harmonic series with this one little alternating thing going on. But if we want to know if it converges, we just run the test. Are the terms of the sequence, where essentially we drop the negatives and consider them all positive, are the terms of 1 over n decreasing? Yes, clearly, 1 over n decreases. Is the limit of 1 over n 0? Yes, clearly. We've done that before. Both conditions are met, which means that one converges. Which essentially means the regular harmonic series 1 over n diverges, but the alternating harmonic series converges. And that can sometimes be a little bit confusing, but if you think about it, it actually makes sense. If I kind of plot the graph of the sum, or actually rather than plotting a graph, we can do it mathematically relatively quickly. If I look at the partial sums, s sub 1 is equal to 1. S sub 2 is equal to 1 minus a half, which is a half. S sub 3 is equal to a half plus a third, which is 3/6 plus 2/6, so that's 5/6. S sub 4, this is where I'm going to stop because I messed up fractions. That's 5/6 minus 1/4. 5/6 minus 1/4. That's 10/12 minus 3/12, so that's 7/12. And then I'm going to add again and subtract and so on. But if we think about it graphically, if I just plotted these sums out, s sub 1 is 1, s sub 2 is a half, s sub 3 is 5/6, s sub 4 is 7/12. And I can kind of see a pattern here. I go down and up, down and up, down and up. But because the terms of this sequence are continually getting smaller, I can never get back where I started. I go up to 1 from 0, and then I subtract a half, so I never get back to 0. Then I add on a third, which is smaller than a half, so I never get back to 1. Then I subtract off a fourth, which is smaller than a third, so I never get back to a half. And clearly what's going to happen is that I'm going to keep on adding and subtracting, and eventually I'll close in on some number here. There are actually mathematical ways to calculate this. I'm not going to put it in this video because it'll end up being too long, but I'll make another video where we kind of mess around with this a little bit. But if nothing else, it should be clear that while the regular harmonic is divergent, it's pretty clear that this alternating harmonic should converge just looking at the partial sums. Two more really quickly. Suppose I have the series n equals 1 to infinity, negative 1 to the n plus 1, times 2 to the n over n squared plus 6. Clearly an alternating series right here, so I run the check. Is it decreasing? And you can plug in random n's. I've mentioned this before, you engineering people like your calculators. You can plug in some random n's, make n 5, 10, 100, 1,000, and see that it's decreasing. it's a linear over a quadratic. Clearly this will dominate, so clearly it will end up getting smaller, which means it'll be decreasing, so that condition holds. And clearly, again, I'm not going to take the time to write out the actual finding the limit of this right here, but it's obvious that's linear, that's quadratic. We have a bunch of tricks to find the limit there. Linear over quadratic, quadratic dominates, which means ultimately this goes to 0. So the terms are decreasing, the limit is 0, it converges, and that's it. The one good thing about this test, it's pretty straightforward. 2 simple conditions, easy to check, you get convergence. Otherwise, you're stuck with something else. So, last one I want to go over. 2n over 4n plus 3. N equals 1 to infinity, negative 1 to the n plus 1, 2n over 4n plus 3. Again, clearly alternating. I run the first check, is it decreasing? Again, you can plug in random n's and actually see this will definitely decrease. The second condition, if I take the limit, well, let's see. If I take the limit of 2n over 4n plus 3, again, we have different checks, but you can actually go back to 171 pre-calc for this. If you think about the function 2x over 4x plus 3, rational function, degree is the same, numerator and denominator, or just divide all these by n, and you'll end up getting the limit is 2/4, which is obviously 1/2. Which means the limit of the a sub n's is unequal to 0, which means for this test absolutely nothing. Because this test can only show convergence with these 2 conditions, since this condition isn't met, the series fail. The test fails. However, if this test fails, if you're using the alternating series test and you get the second condition to fail, that the limit is unequal to 0, well then the limit is unequal to 0. And we have another test, the nth term test, which says if you take the limit of the a sub n's and it's unequal to 0, then the series diverges. So in this case, if you're doing this test and the second condition fails, then generally plug into the nth term test for divergence, and then you'll show divergence. But again, it is important from a mathematical rigor formula way of doing this. You can't say the limit is unequal to 0, so the series diverges. This test doesn't show it. But if you get this and it's unequal to 0, then you say, okay, now I can apply the nth term test, and the nth term test is what actually shows me divergence. Okay, this test is pretty straightforward and works reasonably quickly and reasonably well. Like I said, there is one other thing I want to do as far as this alternating series and kind of messing around with it. So I'm going to do one other video messing around with that a little bit.